Hello and welcome. In the next few minutes, we're going to do a quick introduction to error handling in Rust. We'll start fresh with a new cargo crate and dive straight into code. No slides, no fluff. Rust handles errors and absent values primarily through two important enums. First is option T, which represents a value that might be present or might be absent, basically a safer way to handle what other languages might use null for. The second is result TE, which represents either a success value in OK or a failure value in error. Rust strongly encourages handling potential errors explicitly rather than using exceptions like in Python, Java, or C#. Let's begin by talking about panics. A panic in Rust is used for errors that are unexpected and indicate a bug that the program cannot recover from. When a panic occurs, Rust unwinds the stack or aborts the program entirely and prints an error message. You should avoid using panic for expected errors like a file not being found or invalid input. Panics are generally discouraged in library code but are more acceptable in application binaries or tests. Let's create a function that demonstrates a panic. We'll call it causePanic and have it take an integer parameter. If the input equals 0, we'll call the panic macro, otherwise we'll print something. In our main function, we'll first call this function with a non-zero value like 5, which should be safe. Then we'll call it with 0 and watch what happens. We'll see the program crash with a panic message. Next, let's look at the option type, which handles the possible absence of values. This isn't strictly an error handling mechanism, but it's closely related and very important in Rust. For example, we can have a string and try to find a particular character in it. If we search for the letter A in Hello World using the find method, it will return an option usize. We can use a match expression to handle both possible outcomes. If there's an index, sum, we'll print that index, and if there's no match, none, we'll say that nothing was found. Since Hello World doesn't contain the letter A, we'll get the none case. But if we change our string to Hello Planet, then we do find an A and get the sum case with its position index. This shows how option helps us handle values that might not always be defined. Now let's look at perhaps the most important construct, result TE. This gives us a value on success, OK, or an error value on failure, error. To demonstrate this, let's create a custom error type called DivisionError with a message field and then implement a divide function that might encounter division by 0 errors. Our divide function will return a result that's either a valid number or our division error. If the denominator is 0, we return an error with our division error. Otherwise, we return an OK with the division result. Testing this in our main function, we can see that dividing 5 by 1 gives us a valid value of 5, but dividing 5 by 0 gives us our division error with the appropriate message. An important extension to the result type is the question mark operator, question mark. This operator provides a cleaner way to handle errors by immediately returning them when they occur. Let's demonstrate this with an example. Let's create a function that calls our divide function and uses the question mark operator. If divide returns an error, the question mark will immediately return that error from our function. This makes our code cleaner and simpler compared to manually checking for errors. To show how this works, let's modify our divide function to divide then add 1. With a non-zero denominator, everything works fine. For instance, dividing 5 by 2 gives us 2.5, and adding 1 gives us 3.5. But if we try to divide by 0, we'll get the same division error as before because the question mark immediately bubbles up that error from the divide operation. In real applications, you'll often want to define custom error types that can handle various error scenarios. Let's sketch an enum called math parse error with 3 cases: division error, which we already have, parse error for when string parsing fails, and negative number for when input values are negative. For our custom error type to be user-friendly, we should implement the display trait, which allows for better error messages. We'll match on each error variant and provide a specific message. For division error, we'll say cannot divide by 0. For parse error, we'll say failed to parse input. And for negative number, we'll say input must be positive. We should also implement the standard error trait for our math parse error enum. This requires implementing the source method, which returns the underlying error if there is one. For division error, there's no underlying error, so we return none. For parse error, we return the wrapped parse int error as the source. For negative number, there's no source, so we return none. To make it easier to convert between specific errors and our higher level math parse error, we should implement the from trait. This allows automatic conversion from division error or parse int error to our math parse error. This conversion is used implicitly by the question mark operator. Now let's tie everything together with a function called process inputs. This function takes 2 strings representing a numerator and denominator and returns a result with either a number or our math parse error. Inside this function, we first try to parse the strings into integers. We use the question mark operator here, so if parsing fails, the function immediately returns with the parse error wrapped in our math parse error. Next, we check if either the numerator or denominator is less than 1. If so, we return a negative number error. Otherwise, we call our divide function and return its result, again using the question mark to automatically propagate any division error. This example combines multiple error handling concepts: panics, option, result, custom error types, and the question mark operator, creating a clean, readable, and robust approach to error handling that's ready for real-world use. In summary, Rust's approach to error handling is explicit and type-safe with no hidden exceptions. It uses option T for values that might be absent and result TE for operations that might fail. The panic mechanism is reserved for unrecoverable errors, while everyday issues are handled through the result type. Custom error types and the question mark operator make complex error handling cleaner and more maintainable. This approach might seem verbose at first, especially if you're coming from languages with exceptions, but it leads to more reliable code by forcing you to consider what could go wrong and how to handle it appropriately. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code in the description as well. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.